Okay, sorry for the delay. Again, this is a reminder that the 7th of November, we're gonna have our exam at 7 p.m. So 7th of November at 7 p.m. our exam 2 in this room, ISB 135. Tonight, I'm gonna do a review session, a help session at 6 p.m. ISB 221 upstairs, okay? The last time that I'm gonna take your questions and put it in slides to handle the review session is today at 11 a.m. After that, I'm not gonna take the questions because I have to put it in a slide form. What else? We don't have a class at 8 a.m. 7th of November. Okay, so that's all the announcements. We're gonna get started with the lecture. So the last time we ended our lecture talking about ionization energy, and we said that ionization energy is the energy required to take an electron out of the atom. And we said that this energy is always positive. That means it is an endothermic process because we need energy to take the electron out of the proton attraction. So it is electron-proton attraction, and when I want the electron to take the electron out of the atom, that means I have to put enough energy to overcome the attraction between the proton, which is positive, and the electron that is negative. And we said by definition that that's only for in the gas phase. For the gas phase. So if I ask you what is the equation for ionization energy, it is, first of all, the first ionization energy is taking any element. It can be magnesium, it can be any of those elements in the periodic table. So it's magnesium gas minus 1 electron to give magnesium plus. In the gas phase, it's going from the gas phase as an element to the gas phase as an ion. This is the first ionization energy. And always the first ionization energy is less than the second ionization energy. Where for the second ionization energy, I'm taking the magnesium 1 plus to magnesium 2 plus, both of them the gas phase. So both of those are in the gas, both are on the gas phase. Then definitely the second ionization energy is much bigger than the first ionization energy. Now, definitely when you take the first electron, when you take the other electron, the second electron, there is more attraction, especially if that electron is closer to the nucleus. That implies you need much more energy to get that electron. And definitely the third ionization energy, it's at least 7 times more than the second ionization energy. And it is taking Mg2 plus to Mg3 plus, both in the gas phase. Okay? Now, one thing that you may see either in OWL or in books other than this is that sometimes they move that electron from this side of the equation to this side of the equation, and they put it as a plus. It's the same. So if you see it as magnesium gas, give magnesium plus gas plus 1 electron, it's the same equation. Because if you take the electron from that side of the equation to the other, it's going to be minus 1 electron. So both of these means the same thing. Same. Okay. So this is kind of the definition of ionization energy. Now our second step is to see, is there a trend? Because we learned for radius that the radius increase as I go in the same group, and it decreases as I go in the same period from left to right. So we're going to see, is there a trend for the ionization energy in the periodic table? So here we go. Okay, so as we go down the group, the radius is increasing, right? As the radius increases, that means the electrons are far away from the nucleus, and it is easier to take an electron when it is far away from the nucleus. So as we go down the periodic table, the first ionization energy decreases as we go in the group. So it is exactly the opposite of the radius. So we said that the radius increases this way. The ionization energy will increase that way. It's much easier. It's much easier to take an electron from cesium compared to hydrogen, because in cesium, the outermost shell is far away from the protons in the nucleus, and it is easier to take those electrons compared to a hydrogen, which have the electron very close to the nucleus. So in other words, the ionization trend is exactly opposite to the radius trend in the periodic table. So that's in the period, in the same group. Now we're gonna see as we go through the same period. So here we go. So we said that the radius decreases this way. So the radius decreases if we go this way, right? So that implies that the ionization energy is gonna be exactly the opposite. As I go in the same period, the ionization energy increases. So ionization energy increases this way. Why? Because the radius is smaller, the electrons are closer to the nucleus, therefore it's harder to remove the electron. Okay? So in other words, the trend of the ionization energy is exactly the opposite of that of the radius. The bigger the radius, the lower the ionization energy. The easier is it to take an electron from the electron. Now, this is a very general trend. There are two exceptions that we're going to talk about. So, if we look to the nitrogen in this table, and I'm going to just highlight those two elements in here, the nitrogen and oxygen, we can see that the ionization energy, we said as we go this way, the ionization energy should get higher and higher. If we look to those numbers, the first ionization energy of nitrogen and oxygen, we find that oxygen has a lower ionization energy than nitrogen. Right? And I just said it's the opposite. I said that the ionization energy will increase as I go in the same period. And the reason behind that is if we look to the electronic configuration of nitrogen and oxygen, we find that if I'm going to take an electron from the oxygen, in this case, if I'm going to take an electron, I'm definitely going to take this electron. Okay? And if I'm going to take one electron from the nitrogen, I'm going to take it from here. Right? So what is the difference? What makes the ionization of energy of oxygen lower? Yes. It doesn't have a complete outer shell. Not necessarily, because the ionization energy is all to do with the interaction with the nucleus, right? So if we look to the oxygen right there, we find that the electron that I'm going to take out of this when I do the ionization energy is the one that is paired. That means there is already repulsion between those two electrons. While when I'm taking the electron from nitrogen, I'm going to take it from one that is alone in an orbital. So that repulsion energy between the two, that repulsion force between those two electrons lower the ionization energy, because the oxygen is going to be much happy if you take one of those electrons that are repelling each other already. So this is why the ionization energy of oxygen, is lower than that of nitrogen, because the atom is losing one of the paired electrons. Okay? Let me just put it up there so that you can see that. So this is the first exception of the ionization energy. We're going to talk about the second exception in a minute after you finish writing that. Okay. Now we're going to talk about the second exception. So the second exception is the first ionization energy of beryllium and boron. So again, we find that the boron has a lower ionization energy than beryllium, which is against the trend that I talked about. So if we look to the configuration, the electron configuration of beryllium and boron, I find that if I'm going to lose one electron in this case, I'm going to lose it from a 2p. And if I'm going to lose one electron, which is ionization, from this, I'm going to lose it from the 2s. And this is why it is easier to lose an electron for the boron to lose an electron. Why? Because we're going to take that electron from the 2p rather than the 2s. And the 2p is a little slightly far away from the nucleus compared to the 2s. And this is the reason behind that exception. So in boron, the electron will be lost from a 2p subshell compared to a 2s in the beryllium case. Therefore, 2p is far away from the nucleus compared to 2s. Okay? So those are the two exceptions. It's when we go from beryllium to boron, so group 3a has a lower ionization energy than group 2a, and the group 6a have a lower energy than group 5a. But the trend in general is, as I said, it's opposite to the radius except in these two cases. Okay, so now let's see the trend. Do you still need more time for this one? Okay. Now this is the general trend for the ionization energy, that the ionization energy increase this way and this way. And if I'm you, I'm gonna, at the end of this lecture, we're gonna talk a lot of properties in the periodic table. I would just summarize them in one table. The other thing that we learned about is the radius. We said that the radius increased this way and this way. So radius increase this way, and the radius increase this way. Okay? Now this table in here, shows the general trend of ionization energy. Now this table shows you that the two exceptions, which is that when we go from 2A, this is the ionization energy, that yes, the ionization energy is increasing until we get to group 3A. It has a lower ionization energy, then the ionization energy increases until we get to the oxygen, it's lower than the nitrogen. So this one shows you the two exceptions, which is group 6A and group 3A, that both of these are exceptions. Now in this one, because it's not a colored picture, like it doesn't have the colors green and blue, as in the slides, it doesn't really show up in here. But if you look to the slides, back to the slides, it's more clear. So the two exceptions, 3A has lower ionization energy than 2A, and 6A has lower ionization energy than 5A. And I'm going to put it this way so that you can see that. Those are the two exceptions for ionization energy. Now definitely we can do eye clicker because the laptop is not working. So what I'm going to do is I'm going to just give you 1 minute or so to think about it, then I'm going to discuss that coming eye clicker. Okay? Okay. So rank sodium, potassium, cesium in order of increasing first ionization energy. So we're talking mainly about cesium, about potassium, and sodium. We're talking about those three elements in the ready to discuss it, guys? Are you ready? Yes? No? Yes? Go. So, as we said that the ionization energy increase as I go this way in the periodic table. So clearly, sodium gonna have a higher ionization energy than potassium, than cesium. That's make B the right choice in this case. So B in this case is the right choice. So all what you need to know is the trend, to know how exactly in the periodic table is the trend of ionization energy or of radius or any of those. Now, this is another eye clicker. Again, we're gonna do it the same way. I'm gonna give you some time to think about it, then I'm gonna discuss it. So which of the following chemical equations refer to the second ionization energy of magnesium? Definitely the first one is wrong for two reasons. It's solid. We said that all the ionization energy equations should be represented from gas phase to the gas phase. The second mistake, that even if it's going to be the ionization energy, it must be from the first ion gas to the Mg2+. So definitely this is wrong. Clearly this one, B, is right because it's going from magnesium plus gas minus 1 electron to magnesium 2 plus gas. So this is right. The last one is definitely wrong because we didn't talk in ionization energy that it is the loss of 2 electrons at the same time. So this makes C definitely wrong. Okay? So keep in mind that always whenever we're talking about ionization energy, we're talking equation. It is from the gas to the gas, and we're losing 1 electron in each step. Now, what we're going to talk about is another property. We talked about ionization energy. Now we're going to talk about electron affinity. So, electron affinity, by definition, is the energy change for a process in which an electron is acquired by an atom in the gas phase. In other words, It's when the atom gains an electron, how much energy is released. Because this process is an exothermic process. So the electron affinity is always going to be negative. That means exothermic. All the time. And by definition, it is the addition of one electron to the gas phase of the atom to give F minus. From F gas to F minus, this is the electron affinity. And another example is boron gas plus 1 electron to B minus, and it is always negative, and this is the definition of electron affinity. It's not a complicated thing. It's mainly ionization energy is losing an electron, it's endothermic. Electron affinity is gaining an electron, and it is exothermic. Now let's see the trend in the periodic table. Is it the same as the ionization energy? Is it the same as the radius? How exactly is the trend in the ionization energy? That's for the electron affinity. Okay. So, the element with a high ionization energy has a high electron affinity. So that implies that the trend is the same as the ionization energy. The trend of electron affinity is the same as ionization energy, with another two exceptions, which are 2A and 5A. So as I go in the same period, the electron affinity gonna increase, except for 2A, it's gonna decrease, then it goes up until we go to the 5A, it decreases again. Okay? And the reason behind this difference is in one of these, that's when I go from 4A to 5A, when I'm adding the electrons, I'm gonna pair it. That means I'm gonna put two electrons in the same orbital, and that's cause the repulsion, which make it harder to add that electron. And this is the reason behind these two exceptions in here. Now I just wanna bring your attention that those energies are in minus. So the one for example, the 7A, which is the ones with the higher electron affinity, they have almost minus 300 kilojoule per mole as an electron affinity. This minus means it is exothermic, that this process is giving energy. This is why it is minus in here, minus 300. So always the electron affinity gonna be represented with a minus because it's exothermic, but minus 300, that means it's giving out 300 kilojoule. It doesn't mean it's losing minus 300 kilojoule. Now, as you can see, the 8A, group 8A is not there even. Why? Yes? Very good, because group 8A are the noble gases. They are happy, they are satisfied, they have the octet rule, which is 8 electrons. They don't accept any more electrons. This is why they aren't in this trend. If I ask you what is the electron affinity of noble gas, they don't have electron affinity. They don't accept any more electrons. So let's see what is the total trend, what is the total trend of the electron affinity. Okay, let's see here. So again, this is the electron affinity trend, definitely with the two exceptions that we talked about, but we're talking about the total one. So mainly it's the same as ionization energy. It increases this way and this way. If I put the radius increase this way and this way. Radius increase. Okay. So definitely the ionization energy, I'm going to put it in here also, maybe in the red color. Ionization energy increase, ionization energy increase. Okay, so what we're going to do next is again an eye clicker, a virtual eye clicker about the electron affinity. Okay. which of the following elements has the most negative electron affinity? That means it's gonna give you the most energy because it's exothermic. Is it phosphorus? Is it carbon? Or is it fluorine? So we know that the trend of electron affinity is the same as ionization energy. It increases this way and this way. Therefore, the phosphorus has less electron affinity than the carbon. The carbon has less electron affinity than fluorine. So fluorine is the one with the highest electron affinity. So C is the right answer for this one. And it is the highest negative because it's the most exothermic. Yeah. But that's right, but it is in the period before, so that's make it also more or less. But yes, it is the exceptions, one of the exceptions. Okay. Now we talked about the atom radius, the atomic radius inside the periodic table. Now what we're gonna talk about is the ion. Okay, the size of the ion radius, the ionic radius. So, an example of that, we said that we talked about the ionization energy, and we said, what if lithium loses one electron? This is the electronic configuration of lithium. It is 1s2, 2s1. If it loses one electron, it's going to be 1s2. Now, how would that affect the size of lithium plus? So, if I'm comparing lithium and lithium plus, which one would have a bigger radius? As it is clear in here that the lithium atom will have a bigger radius than lithium plus. Why? Because if you look at the electronic configuration, you find that the lithium has 2s1, so it has the subshell 2s filled. When it loses one electron, it's gonna be this shell this subshell gonna be empty. That means it's gonna be smaller inside. And this is the rule of thumb. Any cation is smaller, has a smaller radius than its atom. Any cation, that means something that lost an electron, any cation has a smaller radius than its corresponding atom. And I'm talking about its atom. So lithium, lithium plus. Sodium, sodium plus has a smaller radius than lithium. And as you can see, the difference is from 152 to 78 picometer, which is picometer is 10 to the minus 12 meter. And this is a rule of thumb, always. Okay? Now, what about... Okay, I'll wait for you to finish writing. Okay. Now, what about an anion? What if we add an electron to an atom? Okay. So let's take the example of fluorine in there. This is the electronic configuration of a fluorine. Then if we're gonna add one electron, that means we're taking it from an atom to an anion, S minus. That means I'm gonna add one electron to this orbital, and definitely when I add the electron in here to this one, there will be two electrons that are paired and they will have some repulsion, and that would increase the radius of the anion. So as a rule of thumb, the anion has a higher radius than its corresponding atom. Okay? And that's a rule of thumb. So always cations have a smaller radius than the atom, and always anions have a bigger radius compared to their atoms. And this is a rule of thumb. Okay. Now, what if I have ions that loses 2 electrons, or cations that they are 2 plus, or 3 plus, or 4 plus? This is what we're gonna check in this next slide. So this is, okay, let me just remind you with one thing. Only group 1A will lose 1 electron. That's a rule of thumb, right? Because if they lose 1 electron, we learned when we learned about the electronic configuration that they're gonna look at the noble gas in the row before it, in the period before it. Only group 2A loses 2 electrons. Group 3A, aluminum loses usually 3 electrons. For 6A and 5A, for 5A they gain 3 electrons to look like a noble gas. 6A they gain 2 electrons to look like a noble gas. 7A they gain 1 electron to look like a noble gas. Now in here, what we have is a group 1A, all group 1A, the cations of a group 1A. That means all of them lost 1 electron. As you can see, all of them, the trend is still the same. We learned that as we go in the same period, the radius increases, right? So if I go from hydrogen to potassium, potassium has a bigger radius than hydrogen. The same in here. Lithium plus has a smaller radius than sodium, than potassium, than rubidium, than cesium. So also the cationic radius increases this way. So the cation radius in the same group increases as we go down in a group. Okay? So the trend is the same, and it is the same for example, 2A, if I'm comparing the 2 plus, but we have to compare the same charge cation. That means I'm comparing lithium to 1 plus, sodium 1 plus, potassium 1 plus. For 2A, I'm comparing magnesium 2 plus to calcium 2 plus to barium 2 plus. Barium 2 plus will have a higher radius, a bigger radius than the sodium. So it is the same case. If we go down this period, if all of them are cations of 2 plus, they're gonna have a higher radius. The barium gonna have a bigger radius than the beryllium. The same for group 3A. Now for 5A only, when we get to the anion side of the periodic table, again the trends keep going the same. As we go down the same group, we're gonna have the radius increasing as I go down the same group, Now, when I'm looking at the cations and the anions, always the anions, if I'm looking in the same period, if I'm looking to the anions and the cations, always the anions is going have higher radius than cations. This is the rule of thumb. Always the anions in the same period gonna have a bigger radius than the cations, than those that lost electrons. So as you can see, fluoride has a higher, bigger radius than beryllium 2 plus or lithium plus. Definitely N3 minus have a bigger radius than the beryllium 2 plus and lithium 2 plus. O2 minus, the oxide has also a bigger radius compared to those of the cations. And you can look all over this, and the trend is the same as you go. Now, what if I'm comparing the cations together? Like I'm comparing sodium to magnesium 2 plus, to aluminum 3 plus. What did you recognize in there? Let me zoom in a little bit. Okay? So when you look to the radius of sodium, magnesium, and aluminum, 3+, which have the smallest radius? Clearly the aluminum 3+, the one with the highest charge, that means it lost 3 electrons, gonna have the smallest radius. So when I'm comparing the cations together, the one with the highest charge gonna have the smallest radius. So for cations, the cation with the highest charge has the smallest radius. And this is another rule of thumb about the cations. So always anions are bigger in radius than cations. Cations, if we're comparing them together, the highest the charge, the smallest the radius. Now what about anions? When we look at anions, so I'm gonna, for example, I'm talking about N3 minus, O2 minus, and F minus, which have the smallest radius. Just look to the numbers. The numbers are there, 146, 140, and 133. The one with the highest charge has the biggest radius. Why? Because the 3 minus, that means it gained 3 electrons. And now it's going to have a bigger radius. So for anions, the anion with the highest charge has the biggest radius. Okay? And that's a rule of thumb. Okay? So those are the 4 rules that you have to keep in mind as you go in the same group. As you go in the same groups and you're comparing the cations, the radius increases. Cations always have a smaller radius than anions. Anions with a higher charge, they have a bigger radius. And I'll see you Wednesday at 7 p.m. for the exam. And I'm waiting for your emails in hand in case you have questions for the review session.